Hello, I'm Julien Cesbron from the Joint Research Unit in Environmental Acoustics at Université Gustave Eiffel in France. I'm going to speak about the acoustical assessment of road surfaces at urban and peri-urban speeds by simultaneous caused by and close proximity measurements. Let's start with the context and the aim of the study. Tire run noise is the main source of road traffic noise, even at low speeds in urban areas, and low noise road surface can be employed in noise mitigation action plans imposed by the European Environmental Noise Directive. So the aim of the study was to test running noise on different road surfaces for vehicle speed between 30 kph and 110 kph, including urban and peri-urban velocities, and then to get the classification and categorization of road surfaces at 50 kph. The idea of the experimental campaign was also to get a noise database for the calibration of tire run noise models, as for instance the statistical hybrid approach developed by my colleague Philippe Klein and I, and which will be presented during the poster session of the FA2020 Congress. Materials and methods. So 15 road surfaces have been tested, and the reference test track in Nantes in France at Université Gustave Eiffel. You can see here a closer view, upper view of the 15 road surfaces, and in the table you have the name of each road surface, the type, and the mean profile depth for each road surfaces. So you have a different kind of road surface on the test track, and the first is A is porous asphalt. Then you have 3 surface dressing of different grading, A prime, C1, C2, and F, and then you have different dense asphalt concrete of grading O10 with different mean profile depths, which are C1, E1, E2, J0, and you have DAC 08, which is isolac road surface. You also have a sand mastic asphalt and smooth epoxy L1 and sand asphalt L2 and 3 very thin asphalt concrete of different grading. For the 3 surfaces A, M2 and M3, the sun absorption was measured, and we obtained here the coefficient, absorption coefficient alpha. It was measured with the ISO 13472 method, which is the extended surface method. And we have measured the average absorption coefficient at 5 different points on the test section. So for road surface A, you can see a peak there between 1250 Hertz and 1600 Hertz. And the peak is of the absorption coefficient is about 0.7. For M2, you have absorption of 0.3 at 1 kHz, and for M3, you have absorption of 0.6 between 1 kHz and 1.25 kHz. The test vehicle and tires. So the test vehicle was a passenger car Renault Scenic, usually used by Université Gustave Eiffel for CPX test. And the tire was, the vehicle was fitted with 4 identical tires, which were Michelin Energy tires, E3A, of size 195/60 R15 tire for the dimensions. Regarding the measurement procedure, the close by and close proximity tests were performed simultaneously, and the CPX was recorded at minus 10 plus 10 meters around the pass-by microphone. So you have here the configuration sketch, and on the right you have the photo of the vehicle passing and the microphone on the roadside. Passages were performed at constant speed, every 5 km per hour, from 30 kph to 110 kph. Regarding the coast-by method, the vehicle was rolling past the roadside microphone with the engine switch off up to 60 kph, and after the speed, so from 65 kph, only the transmission was disengaged. Regarding the CPX measurements, the CPX French method was used, which is confirming the ISO 11892 standard. The analysis of tire noise was quite usual for the coast-by measurement, so we have done logarithmic regression versus speed for overall noise and CB spectral noise between 100 Hz and 5 kHz. So you have here the basic formula for this relationship between the noise levels and the vehicle speed phi. For CPX, it was a little bit more complicated. We have to take care of the airflow noise, and the valid frequency range was determined from the signal to noise ratio relative to airflow noise, which was fixed to 6 dBA. And then once we have fixed this signal to noise ratio, so you have here the different spectra for all the road surfaces, and you can see the airflow noise and the airflow noise plus 6 dB at 50 kph. And with this, we can remove points that are not respecting the 6 dBA signal to noise ratio threshold. So once we got this valid values, we can recompose the global noise levels on the valid frequency range F1 and F2 at speed V. So that's it. And when we have this valid recomposed noise levels, we can do the same regression analysis of the noise levels in the overall noise levels, and in the frequency domain, we can do the logarithmic regression of CPX noise versus speed. Regarding the results now, if we look at the correlation between the coast-by and CPX third octave band noise level, we obtain a very good correlation, including low speed range from 30 from 60 kph, which is relatively new here. Before we did this study from 65 to 110, and we obtained a good correlation. And here, this is confirmed for urban speeds below 65 kph. So in the following, I will only do the analysis from the coast-by noise level. If we look at the coast-by overall noise levels, at 50, 70, and 90 kph, corrected at 20 degrees. The difference between the quietest and the loudest road surface are 11.8 at 50, 12.8 dBA at 50 kph, and 13.6 dBA at 90 kph. So we can observe that the difference between the quietest and the loudest road surface is increasing with speed, but in a relatively small amount of dBA. Then from this ranking of the different road surface, we propose 4 categories of road surfaces. Road surfaces in red, including M3, A, and M2, which are covering a range of 2.8 dBA at 50 kph. Quasi-smooth road surfaces in magenta color, which are C1, N, and L1 surfaces, covering a range from 2.4 to dBA at 50. Then we have intermediate dense surfaces, covering a range in black, covering a range of 3.3 dBA at 50 kph, and we have rough surfaces FA'(C2) covering a range of about 7 dB at 50 kph. Regarding the caused by regress noise spectra at 50 kph for the 4 categories, you can observe that for each categories the spectra are quite similar, and have different, but different categories have a very particular shape, especially for the porous surfaces in red or the quasi-smooth road surfaces in red. You can observe some peaks or some noise abatements that are not visible for the 2 other categories. Let's turn to the conclusion. Simultaneous measurements of caused by and CPX noise levels at vehicle speed ranging from 30 kph to 110 kph have been achieved within this study, and special care was towards immunity of CPX data with respect to airflow noise was done with, and the signal to noise ratio threshold was fixed to 6 dBA. We obtained very good correlation between CPX and caused by noise levels in the spectral domain over the whole speed range. And based on caused by noise levels, an acoustical classification of road surfaces was obtained, and this classification is few influenced by the vehicle speeds. And finally, we have obtained a categorization of road surfaces based on characteristic spectral shapes, porous surface, quasi-smooth surfaces, intermediate dense surfaces, and rough surfaces. I would like to acknowledge ADEM, which funded this this work, which was performed within the framework of the I-Suite Code SF project funded by the French program Advancements of Future. Thank you for your attention. If you have questions, I will be happy to answer your questions.